Welcome to HP Tuner's Ford Gen 1 Coyote Training Part 14. In this training module, we're going to take a look at the closed-loop fuel control that's going on inside of our Ford PCMs. The closed-loop fuel control utilizes our front primary oxygen sensors to feed a signal back into our PCMs. Our PCM can then take a look at the target versus the actual reading and then make changes in a short and a long-term fashion. We're going to learn how these both fit together and how we can use this into our calibration strategy, tuning our fuel delivery for our Ford PCMs. We're gonna have a lot to cover. Let's jump in so we can check this out.
Okay, so let's get started. We're gonna be taking a look at working with our closed loop fuel correction in our Gen 1 Coyote applications. Our closed loop fuel correction is going to be taking a look at our front oxygen sensors and reporting back a registered lambda amount to the Ford PCM. It's going to be comparing the measured lambda coming from our front oxygen sensors, comparing it to target lambdas that we're programming in our target lambda tables. It looks at the percentage of difference between the measured lambda and the target. It'll then correct the injector pulse width output so that we're correcting our fuel mixture so that we're going to then have our actual lambda meet our target lambda that we're programming. So it's a closed loop type of correction. Now this relies on the oxygen sensors working properly and that there's no exhaust leaks before or immediately after the sensors. Everything is working properly, then the closed loop correction will be very accurate, and we're going to find that we always hit the target lambda that we're requesting in our program target lambda tables. So we're going to be taking a look at those tables. We're going to be taking a look at the differences in short and long-term fuel correction in our closed loop correction in this tutorial. We're also going to be taking a look at some log data within our VCM scanner so we get an idea what to spot when we're analyzing data in the VCM scanner in our actual data log. So this is going to be just looking at things in general terms. We will be learning how to integrate and work with the closed loop fuel correction for calibration and tuning purposes. We're going to go and take a look at that in future tutorials, but for right now we're just trying to dig in at understanding the basic fundamentals. So let's take a look at some of the tables here that we're going to be programming and working with in terms of our target lambda, and then we'll talk about moving into the VCM scanner and taking a look at analyzing the data. So I have a 2013 Mustang GT file that's open here. You can open up pretty much any file. They're all going to be pretty much comparable to each other in terms of what we're covering here and looking at in the tutorial. If we jump up here to engine and we go here and we move across in our tabs into our fuel tab, we're going to find here that we have a tab called oxygen sensors. We also have a tab called open loop base and power enrichment. The open loop base and power enrichment is where we specify the target lambda amounts. That's what we want to run our target lambda at so we have proper fueling to the engine. So if we look here under open loop base, we'll find that at idle and part throttle cruise conditions, we're going to be sourcing our target lambda amount from our fuel base cold table. If we look at the values in the table, we're finding here essentially from 90 degrees Fahrenheit and warmer intercoolant temperatures across various different load ranges. This is idle 0.15 load all the way up to 0.87, that's full throttle. We'll find that in this range, if our load and our throttle thresholds are low enough, we will be referencing the target lambda that we're programming here as 1.0 or stoichiometric. We'll find in this situation, this gives us a balance of good fuel economy, good emissions output, and power output out of the engine. So we always want to shoot for and run at stoichiometric when we're in part throttle and cruise type of conditions. So we'll find this is where we specify what we want to run at in those conditions. And we'll again take a look at the front primary sensors. There's a front and rear set of sensors. The rear sensors are after the cat. The front sensors are what we look at in terms of the actual reading. So we look at the measured lambda, we compare it to the target that we're requesting here, and the difference between the measure and the target will be, let's say, a couple percent. That's the percentage that we need to adjust our injector pulse width that we're sending out to the injectors by so that we hit the target lambda that we're registering right here. So the closed loop correction is going to be a way that we can go and absorb any kind of errors that are lying in either the fuel modeling side of things or the airflow modeling side of things. Remember, we have our underlying equation, fuel mass is equal to air mass divided by target air fuel. So let's just say we're specifying the target lambda. We know that translates into a target air fuel. We've talked about in a separate tutorial. But the air mass is going to be registered. We'll divide it by the target lambda, target air fuel. We'll get a fuel mass. If we're finding that if our injector data is wrong or our airflow modeling is wrong from our MAF curve, it can lead to an error, meaning we have more or less fuel being delivered to the engine from the target. In that error, we'll make that difference up with the closed loop. So the closed loop is going to allow us to compensate for small deviations and errors. We shouldn't find large outlining errors, 20, 30% errors. We definitely want to go and fix that problem when and if that comes into play.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.